why the fit exists at all. There is no record of an agreement between the universe and the human mind. No negotiation preceded the moment when symbols written by people began to predict eclipses, spectra, particles, and forces. Mathematics was not requested by nature, yet nature responds to it with astonishing precision. Equations invented for internal consistency end up describing external reality. Abstract symbols, defined without physical meaning, generate predictions that experiments confirm to extraordinary accuracy. This is not an aesthetic curiosity. It is a structural fact about modern science, and it is deeply strange. This strangeness is often softened by familiarity. Physics students grow accustomed to the idea that nature follows laws and that those laws are mathematical. But this language hides a problem. Laws are human constructs. Mathematics is not extracted from nature the way ore is mined from rock. It is assembled, definitions chosen, axioms fixed, rules agreed upon. Nothing in the universe demands that space be described by coordinates or motion by equations. These are choices imposed by humans. And yet, once imposed, the universe behaves as if those choices were appropriate. Few physicists were more aware of this tension than Richard Feynman. He did not treat mathematics as a sacred language of reality, nor did he believe that equations reveal what the universe is. To Feynman, mathematics was a tool remarkably effective, profoundly useful, and ultimately provisional. The real mystery was not that mathematics exists, but that it survives experiment. Physics does not begin with equations. It begins with regularities. Objects fall, light bends, charges interact. Mathematics enters only after patterns are suspected. Symbols are assigned, relationships are proposed, consequences are calculated. At every stage, the connection between math and reality is imposed, not discovered. If the predictions fail, the mathematics is discarded without apology. The universe is never blamed. This is why the effectiveness of mathematics can be misleading. It creates the illusion that math governs nature, when in fact it is continuously tested against it. Models that fail vanish from textbooks. Models that succeed are refined, extended, and remembered. Over time, this selection process leaves only the survivors. What remains looks inevitable, even though it is the result of constant elimination. The physicist Eugene Wigner famously described this situation as the unreasonable effectiveness of mathematics. The phrase endures because it captures a discomfort scientists rarely resolve. Why should a system of symbols developed for internal coherence align so closely with external reality? Feynman accepted the discomfort but rejected metaphysical answers. He did not believe mathematics was embedded in the universe, nor that humans were uncovering a pre-written cosmic code. The success of mathematics, in his view, required no deeper explanation than relentless empirical filtering. Mathematics works because it is flexible. When old structures fail, new ones are invented. Euclidean geometry yields to non-Euclidean geometry. Classical mechanics gives way to relativity and quantum theory. Nothing about these transitions suggests inevitability. They reflect adaptation. The universe does not adjust to mathematics. Mathematics is adjusted to the universe. Yet this explanation is incomplete. There are moments when mathematics does more than fit known data. It predicts phenomena no one was looking for. Entire classes of particles, interactions, and effects emerge from equations before experiments confirm them. These predictions are not retroactive adjustments. They are forward-looking consequences of formal consistency. Feynman acknowledged this without mysticism. Once a mathematical structure is constrained tightly enough by experiment, it begins to generate implications that exceed human intuition. The equations are not intelligent. They are simply unforgiving. Human intuition evolved for survival at macroscopic scales. Mathematics has no such limitations. It follows rules wherever they lead, regardless of how strange the destination appears. When intuition and mathematics disagree, physics has learned to trust mathematics because the universe does. Still, Feynman refused to mistake success for revelation. He emphasized that equations describe behavior, not essence. They tell us what happens, not why reality has the structure it does. Physics advances by compression, not completion, by reducing experience to predictive form, not by uncovering ultimate meaning. The real puzzle, then, is not why the universe obeys mathematics, but why it allows itself to be approximated at all. That allowance may be local, conditional, and temporary. There is no guarantee it extends indefinitely. Mathematics has worked spectacularly so far, but nothing in science promises permanence. For Feynman, this was not a cause for unease. It was a reminder of discipline. Mathematics is powerful precisely because it is expendable. It earns its place through prediction, keeps it through accuracy, and loses it without appeal when it fails. The universe remains under no obligation to cooperate. That it has to this extent remains astonishing. Where mathematics stops working. If mathematics truly governed the universe, it would never fail. But failure is not rare in physics, it is routine. Equations break down at extremes. Predictions diverge. Quantities explode toward infinity, and calculations return meaningless results. These failures do not occur at random. They appear at the boundaries where existing mathematical descriptions are pushed beyond the conditions under which they were constructed. The universe does not malfunction in these moments. The models do. For Richard Feynman, this distinction was essential. Mathematical breakdowns were not metaphysical crises, they were diagnostic signals. They indicated that physicists were asking questions their tools were not built to answer. When equations produced infinities, Feynman did not interpret this as nature becoming infinite. He interpreted it as ignorance becoming visible. Infinity, in physics, is not a deep truth. It is a confession. Classical electrodynamics predicted infinite self-energy for point charges. Early quantum theories produced divergent integrals that rendered predictions unusable. These infinities did not correspond to anything observed. They marked the failure of the mathematical framework itself. Nature, when measured, remains finite. Only the descriptions collapse. The most successful response to this problem was renormalization, particularly in quantum electrodynamics. The procedure works. Its predictions match experiment with extraordinary precision, but the method is mathematically unsettling. Infinities are subtracted from infinities, parameters are redefined, and only the final finite results are compared with observation. The technique saves the theory without explaining why it should be valid. Feynman accepted renormalization because it worked, not because it made conceptual sense. He never treated it as evidence that mathematics was revealing something fundamental. To him, it was a workaround, effective, provisional, and suspicious. These episodes undermine the idea that mathematics is the underlying structure of reality. If it were, it would not require such repairs. Instead, physics advances through effective theories, models that work within limited regimes and fail outside them. Classical mechanics is accurate at low speeds and large scales. Quantum mechanics dominates the microscopic. Relativity governs extreme velocities and gravitation. None of these frameworks claim universality. Each is a local truce between abstraction and observation. Physicists are often tempted to believe that successive theories move closer to a final description. History provides no support for this optimism. Every period of confidence has been followed by disruption. New experiments expose domains where trusted equations cease to apply. The lesson Feynman drew was not that progress is impossible, but that finality is an illusion. Mathematics does not converge toward truth, it adapts to circumstance. Aesthetic judgment offers no protection against failure. Physicists frequently appeal to beauty, symmetry, and elegance as guides to discovery. While these criteria can be useful, they are unreliable. Many mathematically beautiful theories describe nothing in nature. Many effective theories are awkward, asymmetric, and conceptually unsatisfying. Feynman distrusted beauty as evidence. Nature, he insisted, does not care what humans find pleasing. Even within mathematics itself, certainty fractures. The work of Kurt Gödel demonstrated that any sufficiently powerful mathematical system contains true statements that cannot be proven within that system. This result does not directly limit physics, but it destroys the dream of a complete, self-contained mathematical foundation. If mathematics cannot fully account for itself, there is little reason to believe it fully accounts for reality. Modern physics increasingly operates in a state where mathematical success outpaces conceptual understanding. Equations deliver correct predictions while their interpretation remains disputed. Quantum mechanics is the clearest example. The formalism works. Its meaning remains unsettled. Feynman was unusually direct about this. He did not believe that hidden clarity waited to be uncovered behind the mathematics. He believed that working descriptions sometimes outrun comprehension. This gap between calculation and understanding is not a failure of intelligence. It is a consequence of scale. Human intuition evolved for direct interaction with the world, not for navigating Hilbert spaces or probabilistic amplitudes. Mathematics functions precisely because it is indifferent to intuition. It proceeds mechanically, following rules wherever they lead. That indifference makes it powerful and alien at the same time. The danger arises when mathematical success is mistaken for ontological truth. Equations begin to feel real rather than representational. Symbols acquire authority independent of experiment. Feynman warned against this constantly. The test is always nature. No equation, however established, is exempt. When prediction fails, mathematics loses without appeal. Failure, then, is not a flaw in physics. It is its engine. Every breakdown reveals the limits of a framework and points toward the need for new abstractions. Mathematics advances not by approaching certainty, but by surviving repeated confrontation with reality. Its effectiveness is conditional, not absolute. The universe does not guarantee intelligibility. It tolerates approximation. For now, the limit is not mathematics. After every successful prediction and every repaired equation, one question remains unresolved: why any mathematical description works at all. Physics can explain how symbols map onto measurements, how equations predict outcomes, how models are refined after failure, but it cannot explain why reality permits this process in the first place. For Richard Feynman, this was not an omission to be corrected. It was a boundary to be respected. The temptation when mathematics fits nature too well is to assign meaning to the fit. The universe is described as mathematical at its core, as if equations were written into reality itself. Feynman rejected this language. He saw it as a confusion between description and structure. Mathematics is not discovered inside nature. It is imposed upon it. That the imposition succeeds does not imply necessity. It implies compatibility. Human cognition evolved as a pattern detection system. Survival favors organisms that identify regularities and exploit them. A universe with no stable patterns would not produce observers capable of mathematics or physics. This does not mean the universe is designed to be understood. It means understanding is possible only where regularity already exists. The effectiveness of mathematics on this view is not miraculous. It is conditional. Physicists frequently anthropomorphize nature. They speak of laws being chosen, symmetries being preferred, systems optimizing outcomes. Feynman treated this language as a convenience, not a truth. The universe does not choose, it does not aim, it does not explain itself. These metaphors persist because mathematics feels intentional, but intention exists only in the minds that construct the models. Even when mathematical descriptions are exact, they remain silent about meaning. Equations predict behavior, not existence. They specify correlations, not causes in any ultimate sense. Physics can compress experience into formal structure, but it cannot answer why those structures exist rather than others. Feynman accepted this without discomfort. He did not expect physics to deliver metaphysics. Every explanation in science rests on assumptions that are not explained by the theory itself. Constants are measured, not derived. Dimensions are accepted, not justified. Laws are inferred, not necessitated. At some point, description stops. Demanding infinite explanation is not rigor. It is misunderstanding the function of knowledge. Understanding for Feynman meant knowing what to expect, not why the universe exists. Mathematics, like any language, has a domain of validity. Languages evolve, fracture, and fail when stretched beyond their design. There is no reason to believe mathematics is exempt. There may be regimes of reality at singularities at the origin of the universe beyond quantum gravity where existing mathematical structures collapse entirely. Feynman anticipated this. He did not believe the universe owed humans perpetual intelligibility. This position is often mistaken for pessimism. It is not. It is discipline. Feynman rejected false certainty, not inquiry. He trusted methods, not conclusions. The success of mathematics did not signal that physics was nearing completion. It indicated only that the current tools were adequate for the current question. Stripped of interpretation, one fact remains. Mathematics invented by humans predicts physical outcomes with extraordinary accuracy. This fact does not require embellishment. It is strange, provisional, and historically contingent. It may persist. It may fail. Nothing guarantees continuity. The universe does not obey mathematics because mathematics is fundamental. Mathematics obeys the universe because humans continually force it to. When it succeeds, it is retained. When it fails, it is replaced. There is no deeper contract. For Feynman, this was not a disappointment. It was intellectual honesty. The universe remains indifferent. Understanding remains partial. Mathematics remains a tool, not a revelation. That this tool works at all is remarkable. That it may someday stop working is inevitable. That boundary is not a weakness of science. It is where science ends.